All right, so in this video, we're going to be taking a curve like this, and we're going to rotate it about the x and y axis, just like we did before when we did volumes of our solids. But on this, we're going to be calculating the surface area. So you can kind of see this makes like a little vase, right? So if you were to paint from here to here, from A to B, that area right there, that surface, what square footage or square meters, what area do you need to cover to paint that surface? So that's what we're going to be calculating, not copying anything. And we're going to do it the same way. We've got to find some shape here that when we rotate it, it gives us a surface area that we can then use an integral to add it from A, oops, went way too quick, from A all the way to B using an integral. So first we're going to focus on just that one surface area that we can then take our delta x to 0, right, and make an integral out of it and calculate the surface area. So what we need to know. So we did arc length in the previous in 8.1, and in order to do that, it wasn't actually equal, it was an approximate, right? We use the distance between 2 points, and we're given this formula. This is what we created using the distance formula and our mean value theorem. So we also need to know the area of a cone area is pi RL, and you can find that very easily using geometry. You can look it up. And then using that, we can then get the area of a frustum, which is basically just the top part or just a solid cut parallel like this. And so what it does is it makes this little like trapezoid here. You see it? And you can see that trapezoid is what's being rotated. So that is what we will draw on here. And the formula for that is 2 pi L R1 plus R2 over 2. And this is the actual formula. What we did is actually made this into a mean, into an average, right? So we can find the midpoint. A midpoint is something that we can use. And you'll see how we use that when we're making our formula. Do you need to know how to make the formula? No, you just need to know how to use it. But understanding where it comes from can help when you get into complicated problems. So if you think about it, we draw our rectangle here. You can see it's a little bit overshooted, right? So if we then draw two little lines like this, right, we can then think of this whole shape as that curve that's going through, right? So I'm going to make it a little bit bigger here. Because again, we're going to take our delta x to 0. Those look horrible. Let's try that again. One goes there. My pen doesn't want to draw straight. And then if you connect it here, you can see what we're making is this shape here. It's just rotated. So if you were to lay this cone on its side, now when I rotate it, right, it would be that same distance down. In fact, let's rotate it in red. This red will stand out. It's going to be rotated like that, and then down here like that, and then that would rotate like that, right? You can see it's making our frustum. So now all we have to do is copy those things down as to what our functions are. And so we have x coordinates here. These are y coordinates, right? And then the distance between them, well, that we already know as delta x. So we can label all of this. So what you end up having here is a height, and then this is a radius 1. This is radius 2. You see it over there. And we just have to label them. So let's do green for labeling. This is radius 1. This is radius 2. And what else do we need? We need L. So this right here is L, right on the top there, that length right there. And then the distance between them we know is delta x. But we don't need them. So we've labeled R1, R2, and we've labeled L. So we have everything we need for this formula. So if we plug those in, what we end up with getting is A equals 2 pi. And then what was our L here? Well, L, again, was the distance between the 2 points. So our L is equal to the square root of 1 plus f prime of c squared. So we can plug that one in now. So that would be the square root, oops, delta x, forgot that, very important. Delta x square root of 1 plus f prime of c squared. And then now our radii. So this right here would just be we have some x sub 2 and some x sub 1, right? And so what I want to do now is take the R1 plus R2 over 2 and plug that in as a whole. So this would have been f of x sub 2, and this is f of x sub 1. Well, if you think about it, what we have here is R1 plus R2 over 2. This is f of x sub 1 plus f of x sub 2, right? All over 2. Does that sound familiar to you? It should. It's the midpoint. So what we're getting here is some m right here. And so that's what we can actually use. This would actually just become f of m, our midpoint. So I can come over here and put f of m, which is the midpoint. So far, so good. All right, good. So we got our L, which we know is the distance between these, and that's our formula from before, right there. That's done. So that was L. Let's actually highlight it. So L is this. And then this is our f of m. And so we have this. All right. So now let's move on. So if you notice f prime of c and f of m, they're both in the middle here. So remember when we did this formula here, right? What we were using for c is that point there that had the same slope. So that would have been f prime of c. So if you follow that down, you can kind of see that our c is like right there. They're very close. And so if you think about it this way, as our delta x is approaching 0, right, because the distance between them is just going to shrink down as we increase the number of these little shapes that we make, just like before. So the limit as n approaches infinity here, our delta x is going to be approaching 0. What will happen is our c and m basically become very, very close. So c becomes approximately m. They become the same thing. So what we can do now is just change that c and m to just some xi value that we want. And they like to use a star on there like that. Okay, so they both are basically xi. And so we end up now with this formula. A equals 2 pi delta x square root of 1 plus f prime of xi squared f of xi. So now we have the same value right here and here. And so we can now just say that this is 2 pi delta x square root 1 plus, and we're going to convert it now into our formula, which is down here. You can see that we have this. And so I'm just going to put it as just our thing, which is just, let's put an arrow as this becomes this as we do our thing off to infinity. So y squared y. So if I rewrite it, I get 2 pi y square root 1 plus y squared delta x. And if you look down here, that's what we have for our surface area. So it's the integral of 2 pi y ds. And what ds is 1 plus dy over dx squared, or dx over dy squared dy. If you remember before, when we did our distance, it doesn't matter if you're plugging in an x value or if you're plugging in a y value. I'm going to draw it and then erase it. So if we had one going this way, this would be x, right? But you would still be plugging in that point, and that point, it would still be giving you this. We'd still have the slope, but that slope would be in respect to y. We would have dx dy here as our slope. So it doesn't matter if you're using, this just doesn't change. You can take the derivative with respect to y or the derivative with respect to x. It's going to work out either way for that. And that's just y. Because again, that is the number we're plugging in, the m and the c. It goes back up. We have to use that value for now. Okay. So that's where our formula basically comes from. Remember, we'll now take this, the limit as n approaches infinity of the sum of all of these different things that are going on in there. So we now know that's the formula for that one shape. And so as we do our n to infinity, right, it's going to shrink it down into a very, very, very thin sliver. And then now we, oops, way too far. We take our integral, and the integral will take it all the way to infinity. So as we apply our limit as n approaches infinity, and then we take the integral, we end up with this. All right, and so the whole point of this is your ds. The reason we write ds is if we have this as a y equals, we use this. If we have it as an x equals, we use this. But the y stays the same. All right, so that's where it comes from. We are using this little trapezoid that rotates to make a frustum, and we use that formula to get it, and it gives us the surface area. So again, all we are calculating is just that surface area here, not the inside, not the volume of this, just the outside of it. That's all this is calculating, is that outside. All right. And you can kind of remember it. Remember we talked about is pi y squared? It was just like a circle. You can see that kind of situation sitting there right now. We have pi y squared. All right. So let's try a problem here. I've got a very, very, very simple one for us to get through quickly so you can see how they're both applied. And then the next video we'll do something a little bit more complicated, but these aren't that bad like I stated. And again, the links are in the notes for these. So find the exact value area of the surface obtained by rotating this from 1 to 5 about the x-axis. So we're going to take this function from 1 to 5, rotate it about the x. So if you click on the link, you'll be able to play with it in Desmos. And we end up with this. So if we rotate it, you can see it makes that perfect frustum. And that's what I wanted to start with. All right, so that you can see what's going on with each of these. So we're going to start with, this is y equals right here. And so we'd have that little shape going up, right, with our line, and then we rotate it. So we're going to make basically a very small version of this is what's happening. And then we take the integral from 1 to 5 to add up all of those small versions. All right, so on each of these, what we're going to first do is find ds. ds is where we start. And so we're going to find dy dx, and then square it, and then add 1, and then square root just like before. And then we will plug it into our integral and find the surface area. All right, so I'm going to zoom in now so we have more room. All right, so for y, we are going to be using y equals 2x. So we need y prime equals 2. And then again, after the y prime, we square it. And you should be good at this from the previous section. So now we square it, and we get 4. And then we add 1 to it. And so 1 plus 4 is 5. And then we square root it, and we get square root of 5. So derivative 2, that's 4, square root of 5. That is now our ds, right? So our ds is this dx. So ds now would equal square root of 5 dx. But you don't even have to write that. All you have to do now is go to your integral and go s equals square root 2 pi, that's not a pi, that's a y, 2 pi y ds. And so this would equal 2 pi. And then what does y equal? It's 2x. So you plug that in. And then your ds is the square root with a dx on the end. So rad 5 dx. Just like that. And then now we have our integral, and we're going from 1 to 5 for our x. Just like that. All right, so if we take out the 2 pi, that'd be 4 pi rad 5, and then integral from 1 to 5 of x. Of x dx. So let's double check that. 2 times 2 rad 5 pi x. Okay, so then we end up with 4 pi rad 5 and then 1/2 x squared. And so the half will cancel, and we end up with 2 pi rad 5. And then we're going to plug the 5 and the 1 into the x squared. So 5 squared minus 1 squared. So 25 minus 1 is 24. So we get 48 pi rad 5. All right, and so that would be the surface area. So rotating this solid, that surface area from 1 to 5. So that surface that was rotated around there. You can kind of see it here. Let's go the other way. There. Oh, this is very finicky, especially when I'm doing other things, so it slows it down. Take it back. All right. So that surface right there is what we just found. All right, so now we're going to try it the other way, and we're going to solve this for x. So x would just be 1/2 y. And to show you how it's just a similar one, we're now going to take this and do the same thing, but this time we're going to find x prime. So we're going to be doing dx dy. So x prime equals 1/2, and then we square it. And so that would be 1/4. So 1 plus x prime squared is equal to 1 plus, let's just put 1/4, which is 5/4, and then we square root it. So it'd be square root of 5/4, which is the square root of 5 over 2. And then now we plug it in. So s equals integral 2 pi y ds. See, it doesn't change. It's 2 pi y ds because we're rotating it about the x-axis. So same exact formula. So now we get the integral of 2 pi. And on this time, we don't change y because if you look at our formula up here, we just took this with respect to y. And so we're going to end up with a dy. You see how they match right here? Since we took this with respect to y, that's a dy when we would find that formula. So we leave the y alone. And so what this becomes is our ds equals rad 5 over 2 dy, since we took the derivative with respect to y. So we end up with rad 5 over 2 dy. But now you can't use 1 to 5. So our x is from 1 to 5. Now we need to know what our y is from. And so we just need a formula that we can input x's into that gives us y's. And that's right here. You see it? It's sitting right next to it, or you can use that one. So if I plug 1 into this formula, I get 2 times 1 is y. So we're just using the y equals 2x. So that would be 2 times 1. And then over here would be 2 times 5. And so our y will go from 2 to 10. So if we go from 2 to 10, we now have our integral. All right, so these cancel. And so we get pi rad 5. Oops, wrong color. Let me change it back. I don't know how it changed. Pi rad 5 integral from 2 to 10 of y dy. Okay, so this again would be pi rad 5 1/2 y squared from 10 to 2. So this is pi rad 5 over 2. And then we would do 10 squared minus 2 squared. And so that would be 100 minus 4 is 96. 96 divided by 2 is, you guessed it, 48. So we get 48 pi rad 5, exact same answer as we have there. So the whole point is that these are the same. Well, they're not the same, but it's the same formula. It's 2 pi y ds. So if we're rotating about the x-axis, we're going to be using this formula because that's how it was formed from that. And so all you have to do is, if it's given to you in terms of y, you just leave it alone and use it in terms of y. You'll end up with a dx because everything else will be x's. And you're taking with respect to dx. See how they match? Just make sure they match. And so if you do this one as x prime, well, then it's going to be in terms of y. There you go.